Hello friends, today I am starting with a lecture on nucleation and growth. Till now we discussed all the transformation. Okay, first we discussed about the phase diagram, and then using phase diagram we discussed about the transformation from one phase to another phase, how this transformation is going to take place and so on. Okay, but we did not discuss anything about the rate at which this transformation is going to take place. Okay, so now the lectures which we are going to have, okay, basically we are going to discuss about that how this transformation is going to take place. Okay, so this today's course is on nucleation and growth. Okay, so you can understand that when for example, you must have seen the formation of ice from water, okay, when you keep water in the freezer. Okay, so there has to be some place where the nucleation is started and that nuclei is growing. Okay, so always whenever you have any kind of transformation, there has to be some nuclei which is taking place, or some nucleation event has to take place. Okay, and that nuclei will then grow. Okay, and then it will take up the whole space. So from liquid to solid, okay, or you can have solid to solid transformation, as we saw in case of steel, from austenite to ferrite, austenite to pearlite, okay, or from solid, that means from liquid phase to solid phase, okay, and during solidification. So in this all processes there has to be some formation of a nuclei, and then nuclei will grow. In solidification, for example, okay, the vessel in which you are pouring the liquid metal, okay, that vessel wall itself act as a site where the nucleation will take place. So nucleation starts from the wall and then the growth goes inside the molten metal, inside the basically inside that vessel, okay, and then the whole liquid metal will solidify. And that is what if you do a close examination of formation of ice in your freezer, you will see that it is starting from the walls, okay, and it is then going inside the so the central part will be the last one to solidify. Okay, so that is what is the nucleation and growth process. Okay, and from that also we will like to bring the time factor in the whole of this transformation process. Okay. So just to again bring the idea of if you remember when we were discussing initially that the carbon exists in form of hexagonal graphite, okay, as you can see here. Okay, so you have a hexagonal graphite here and you have cubic diamond here. Okay, so if you see, this is a pressure temperature scale, is temperature and pressure. So at lower temperatures and lower pressures, means our normal room temperature pressure, actually the diamond is not the stable phase, it actually should transform to graphite maybe. Okay, so but we said that it does not happen, diamond remains as a diamond for if a diamond was excavated sometime 2000 years back also, it still remains a diamond. Kohinoor is still a diamond. Okay, so it has not transformed into graphite in so many years. Okay, that means it is a still a stable form of that. Okay, and we said that why it does not do that is because the rate of changing from this diamond to, let us say, graphite is very slow. Okay, so that means there is a concept of rate here, a time factor is here. Okay, and that is what we like to understand. So phase diagram, when we see, these are based on thermodynamics principles. Okay, so there is no mention of time here. Okay, only it will tell you that at this particular temperature, pressure, okay, for this composition, okay, whether for this particular system, which phase is the stable phase. Okay, so if you take pure water at room temperature, okay, under normal atmospheric pressure, it should be the stable phase is water, liquid water. Okay, If I take this water above 100 degree Celsius, then the stable phase is the vapor phase. If I take it again at the atmospheric pressure, again I bring it to a temperature below 0 degree Celsius at normal atmospheric pressure, the stable phase is the solid phase. So, thermodynamics tells me that which is going to be the stable phase at a particular temperature pressure condition, but it is not going to tell me about the how much time it is going to take place for the transformation, for example, from liquid to solid phase. Okay. So, it will not give any information about the rate of transformation, so that how fast or slow the transformation will proceed. Okay. That is the domain of kinetics. So, this is the next concept which is called kinetics. So, you have thermodynamics which tells me that which phase should be the stable phase, and then there is a kinetics which tells me that how fast or slow this phase will change from this particular state to the another state. Okay. So, if you see transformation, the transformation involves two processes. Okay. One is nucleation. Okay. That means when liquid is transforming into solid, or one solid is transforming into another solid, there has to be some nucleation. At some point there has to be some nucleation, and then that nuclei, so there has to be a formation of embryo of the new phase which attained critical size and therefore are stable to grow, and then you have a growth process, further increase in the size of stable nuclei of the new phase. Okay. So, this is what is the process of transformation, nucleation and growth. Okay. Now, if we come to nucleation, the formation of new phase from parent phase. Okay. So, suppose I start with a liquid. Okay. Now, the question is when I am bringing down the temperature. So, I am bringing down the temperature here. Okay. So, in this liquid, in this system here, okay, this is my system boundary and there is a liquid inside. So, where this nucleation is going to take place? Is it going to be homogeneous nucleation? That means that the whole liquid everywhere, as soon as I bring down the temperature, at every point there will be some nuclei which is forming of solid. Is it going to be like this? Okay. Or it is going to be heterogeneous nucleation. Okay. That means if this is my system contains the liquid, the nucleation will take place, for example, at the surface of this system. Okay. It can be a vessel or whatever. So, when I bring down the temperature here, okay, the nucleation is starting from here, then it will grow, okay, inside, okay, and later on the whole liquid will transform. So, it can be either homogeneous nucleation, means throughout the system the nucleation is taking place, or it can be heterogeneous nucleation. Okay, that means only at few location the nucleation will take place. Okay, and actually what decides this this whole process, and you will see that most in general the heterogeneous nucleation is the one which is going to be dominating. Okay. To achieve a homogeneous nucleation, actually you have to have very specific conditions, only then you will have homogeneous nucleation. In fact, it is a very difficult process to do, to have homogeneous nucleation, and the reason is, okay, so suppose let us say I draw a free energy curve here, color of the pen here, for example. So, suppose you have two axes here, one axis I am saying is axis, y axis is delta G axis, and the x axis is the radius of the nuclei. Okay. So, delta G is, suppose my liquid is not the stable phase, so my system want to go into solid phase. Okay. So, there is a free energy of the liquid phase, and then there is a free energy of the solid phase. Delta G will be equal to, let us say it will be Gs minus Gl. Okay. So, what is the change in free energy? And if you remember earlier also that we said that the transformation will take place only when the free energy change is negative. Okay. So, this is at this point it is 0, okay, and when the transformation will take place when the free energy is negative. Okay. But the problem is that when you want to have a new phase coming, okay, what will happen? You will have a new interface is there between solid and liquid. Okay. So, some change is there because of the stable phase is solid now. Okay. So, there is a decrease in free energy, but there will be also an increase in free energy because of the formation of the interface. Okay. So, all this will what it does is that it actually increases the free energy initially, and then the free energy decreases as the solid is growing. Okay. So, as a function of radius, if I want to see, okay, I can have a small nuclei which is forming, okay, and then it grows and become a bigger nuclei. Okay. So, I can draw a free energy diagram, okay, like this. My drawing is not very good here, okay, but it will have some curve like this. Okay. So, you can see that initially when the transformation is taking place, the free energy is becoming positive, and then after some time it is becoming negative. Okay. So, this increase in the free energy and reaching the maximum, okay, this will I will call it as, this is known as delta G star, and at the radius at which you have delta G star is called R star. Okay. So, I will have a stable nuclei only when I have crossed this heel, and this is what I call as activation barrier. Earlier also we used this term. Okay. So, this is the activation barrier for formation of new phase from the old phase. Okay. So, this much activation barrier you have to cross to go into the next phase or to have the transformation. Okay. And at this point the radius of the your nuclei will be equal to R star. So, if my radius of the nuclei is below R star, then I will call it as embryo. That means it is not a stable nuclei, it can again go back into liquid phase. If it crosses this critical radius R star, okay, then it will become a stable nuclei, and then the free energy will start coming down, okay, and then it will become negative later on. Okay. So, this is how the change in the free energy is there when we transform from one solid to another solid, one phase to another phase. Now, how homogeneous and heterogeneous nucleation will come into picture in this? Suppose this is a curve for homogeneous nucleation, okay, then for the heterogeneous nucleation, the curve will look something like this. Okay. That means the R stars remain the same, but my activation barrier has come down. Okay. So, when I provide heterogeneous nucleation site, okay, what I am trying to do is I am trying to bring the activation barrier down. So, I now require a small driving force for changing from one phase to another phase, and that is why heterogeneous nucleation is the dominant nucleation mechanism when you have phase transformation. Okay. Of course, these curves you look into in the books, okay, because I am not able to draw it very nicely here. So, if you want to look at heterogeneous nucleation sites, okay, of course, I am not talking about solidification now, I am talking about in transformation in solid phase. Okay. When you talk about the transformation from liquid to solid, the vessel wall is a very good nucleation site. Okay. If there are some foreign impurity particles are there, then they can act as a nucleation site. When you have transformation, so this is solid to solid transformation. Okay. So, in this case we are talking about solid to solid transformation. So, nucleation sites are the non-equilibrium defects. Okay. So, you have either excess vacancies. Okay. Vacancies are equilibrium defects, but when you have excess vacancies more than the equilibrium vacancy concentration, so of course that is not a equilibrium condition. So, then we will call it as non-equilibrium defects. Okay. Otherwise, equilibrium vacancy defects are the equilibrium defects. That is thermodynamically it is a vacancies have to be there. Okay. So, excess, if you have excess vacancies, that can act as a heterogeneous nucleation site. Dislocation can act as heterogeneous nucleation site. Stacking faults are there, grain boundaries are there, inclusions are there. Okay. Already inclusions are present on which you can have another phase forming, or you can have free surfaces on which the nucleation can take place. Out of this, the grain boundary is one of the most important nucleation site. Okay. Because first thing is that it has very good potency, you can see the potency of the nucleation site is increasing. So, free surface is the most potent site and excess vacancies are the least potent site. So, grain boundaries are highly potent, and the second thing is that in the material there are large number of grain boundaries. So, if you want to see the concentration of the sites, the grain boundary sites will be in very high concentration. Inclusion and free surface can be only on the outside. So, for a given volume the amount of free surface will be very less. Inclusion also, if your material has impurities, only then inclusions will be there. So, the grain boundary is actually one of the most important heterogeneous nucleation site. Okay. Now, coming to growth. The growth is given by equation called Johnson Mehl Avrami Kolmogorov equation, JMAK equation. Okay. Or simply we call it as a Avrami equation. And the characteristic of this is that it gives you a typical S curve. Okay. Which what it shows is that the growth kinetics are slow initially at first, and then it accelerates, and then at the end it decelerates. So, this is the typical growth kinetics you will find out in large number of systems. For example, if you want to see a bacterial growth, then also you will have similar S curve. Okay. So, S curve you will see in large number of different systems. So, it is a very common system or common characteristic, and it is given by an Avrami equation. Okay. And the fraction as a function of time will be given by an exponential expression like this, where Ft is the fraction transform, K contain both nucleation and growth terms, and exponent n depend upon geometry of the transformation. Okay. So, you do not have to worry about that right now. So, all these things will come into the overall growth kinetics. So, this is what your typical S curve will look like. So, this is on the x axis you have fraction transformed. Okay. So, 1 means it is fully transformed, 100% transformed. Okay. There is some gap up to which time you will not have any transformation. So, this is you can understand as a nucleation gap. Then this is the first, it is slow as we told you, then it accelerates. Okay. Then it becomes goes into a steady state condition, and then it decelerates and become very slow at the end also. So, initially also it is slow, and at the last stage also it is slow, and it has maximum growth kinetics in this central part. Okay. So, it is a typical S curve you will usually see in lot of transformation, one of and you will see it in the our phase transformation also. Okay. So, as a function of time, what is the fraction transform is what is shown here. From that, okay, from the idea of nucleation and from idea of growth, okay, we can say that you will have some rate of nucleation. So, this is the equilibrium temperature, okay, below which the phase transformation will start. Okay. So, nucleation will start after you do some amount of undercooling. Okay. So, I use this word during solidification also. So, some amount of undercooling will be required, undercooling. Why we have to have undercooling? Okay, to provide driving force for nucleation. Why we need driving force? To overcome activation barrier. Okay. So, there is always going to be some undercooling is required to start the transformation. Okay. That undercooling will give you the driving force for transformation, and that driving force is required to overcome the activation barrier as we just discussed. Okay. So, this is your nucleation kinetics. So, initially it will be there will be some undercooling. As you bring down the temperature, the nucleation rate will increase, okay, because now you are giving more driving force. As you keep on decreasing the temperature, the driving force will increase, but it will saturate at certain temperature, and then it again the nucleation rate will start decreasing, because the diffusion of atoms which is required to make the nuclei stable, okay, the diffusion becomes very slow. So, again it will come down. Similarly, you will have in the growth, okay, the growth rate will also increase as you bring down the temperature, then it saturates, and again as the diffusion becomes slower, the growth rate will also decrease. Okay, and if you combine both the nucleation and growth, you will have a overall transformation rate. Okay. So, it as a function of temperature, okay, as you bring down the temperature, the transformation rate will increase, become maximum at some intermediate temperature, and then it start decreasing, okay, as you bring down the temperature. So, this is the overall transformation rate, okay, combining both the nucleation rate and the growth rate, okay, to give you that how the transformation will show how the transformation rate will change as a function of temperature. Okay. With that, I would like to say thank you, and now using this transformation rate, okay, in the next lecture we will come to a very important topic which is on time temperature transformation curves and continuous cooling transformation curves, one of the two very important topics in the transformation phase transformation, okay, especially when you go to steels. Okay. So, using this idea of the overall transformation rate, we will try to understand the TTT and CCT curves. Okay. Thank you.